Hi, I am Dr.R.Malini Devi, Associate Professor of Mathematics, PG and Research Department of Mathematics, the Standard 5 was Rajaratnam College for Women, Sivagasi. Now we are going to see the topic types of matrices in linear algebra. You see that some types of matrices and properties of these matrices. Now we see that learning objective of types of matrices. To learn about the matrices, next to know about the types of matrices, the third one is to identify the differences between the matrices. First we see that the introduction of matrices. Define matrices. Matrices is nothing but the rectangular array of m cross n numbers or numbers. The numbers may be real or complex in the form of m horizontal line. Here m horizontal line is called a row and n vertical line is called a columns. Columns is called a matrices of an order is m by n. So we can write this m cross n matrices. Such arrays is enclosed by bracket, curly bracket or square bracket. Now the m cross n matrices is usually written as in array form. Here matrices A is equal to the first place A11. The element is represented as A first to first column, A11, second element is A12, that is first to second column, etc. up to A1n. Similarly A21, A22, etc. A2n, the last element m rows. So AM1, AM2, etc. AMN. The above matrices is represented by a matrix A equal to Aij of m cross n. The number A11, A12, etc. is known as the elements of a matrices A, where Aij belongs to that, the I represents the row and J represents the column and is called the ijth element of a matrix A is equal to Aij. Next we see that types of matrices. First we see that row matrices. Row matrices means and matrices is of the form 1 rows and n columns. 1 cross n matrices A is called a row matrices. Thus a row matrix consists of 1 rows and n columns, that is A11, A12, A13, etc. A1n. This is an example for row matrices. Here the row matrices of order is 1, that is 1 rows and 3 columns, that is A equal to 2, 3, 6. The 3 elements are there. So 1 rows and 3 columns. Next we see that column matrices. Column matrices means m columns and 1 rows. And m cross n matrix A is called column matrices. This column matrices consists of m rows and 1 column. Here A equal to A11, A21, etc. AM1. This is an example for a column matrices. The column matrices of order 3 cross 1. Here 1 columns and 3 rows. There are 2 first row, 3 is also second row, 6 is also third row. Here the column is 1. So first we see that row matrices, next one is column matrices. Next means the square matrices. Next we see that the square matrices. Square matrix is nothing but is a matrix. First it is a matrices. Matrices means m cross n arrays. A square matrices is a matrices that has an equal number of rows and columns. A square matrices contains number of rows is equal to number of columns. That is m equal to n. M rows, n columns, we use that m equal to n equal to m. In mathematics we use that m cross m matrices is called a square matrices. Here the order is m. If we multiply or add any two square matrices, the order of the resulting matrices remain the same. This is an example for a square matrices. Here the matrices x equal to, we see that 3 rows. The first row contains 2, minus 7, 7. Next row is 2, 5, 6. The third row is 5, 4, 3. So the column is also 3 columns, 2, 2, 5, minus 7, 5, 4, 7, 6, 3. Here 3 rows and 3 columns. So this matrices is called square matrices. Square matrices has an equal number of rows and columns. This is called a square matrices. Next one is diagonal matrices. The diagonal matrices first is a square matrices. The square matrices is said to have a diagonal matrices if all the entries which do not belong to the principals are 0. That is, the diagonal matrices Aij equal to 0 if I not equal to j. So we see that example, the diagonal matrices D. The first element is A11. In the place of A11 is equal to 1. A11 is, in here definition, Aij equal to 0 is A12, A2, A12, A22, A3, so etc. So first one is A11. So this I and j are equal, so you have any element in that place, we write it 1. Next element, next place is A12. 1, 2 is I is not equal to j, 1 is not equal to 2, therefore we put 0, that is Aij equal to 0. The third place is A13. 1 is not equal to 3, therefore we put 0. Second one, the second row can return as A21. 2 is not equal to 1, so we put 0. The second place A22. A22 means I is equal to j. I is equal to j, we write any number. So only for the diagonals, only for the diagonal elements are 0. Only for the diagonal entries are values, other elements are 0. That is, which do not belong to the principles are zeros. Which do not belongs to that principle. Other than diagonal elements, we get the 0. This is called diagonal matrices. First we check it. Any square matrices is said to have a diagonal matrices if all the entries which do not belong to the principles. Except the diagonal entries, all the elements are 0 is called the diagonal matrices. Next we see that scalar matrices. Scalar matrices is nothing but the diagonal matrices. Diagonal matrices means first it is a square matrices. So square matrices, then we have to set the diagonal matrices. Then the diagonal matrices is said to have a scalar matrices in which all the entries of principal diagonals are equal. Is called as scalar matrices. Here the principal diagonals, except the diagonal entries are 0, the diagonal entries have a same numbers. The entries are equal. In a scalar matrices, the entries 4, 0, 0, 0, 1, 0, 0, 0, 4. Here A11 equal to A22 equal to A33 equal to 4. So the diagonal entries have a same values, so it is called as scalar matrices. First we see that square matrices, so it is equal number of rows and columns. Next we see that diagonal entries. Diagonal square matrices is called a diagonal matrices that only have the diagonal elements have a numbers, other entries are zeros. The third one is scalar matrices. Scalar matrices means first of all it is a diagonal matrices in which all the principal diagonals are equal number of element, that is A11, A22, A33 is equal to same. Next we see that transpose office matrices. Transpose office matrices is nothing but interchanging the rows and columns or columns into rows. The transpose of matrices by interchanging its rows into columns or columns into rows. The transpose of the matrices is denoted by using a letter T in the superscript of the given matrices. Now see the example of a given matrices A. Here the given matrices A equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. This original matrices is the original matrices A. You have to find out the transpose, A transpose. A transpose is nothing but interchanging rows and column. We see that the first row 1, 2, 3. Here the first column is also 1, 2, 3. So second row is 4, 5, 6. A transpose column. Here column matrices is 4, 5, 6. The third one 7, 8, 9 in the original matrices. A transpose matrices 7, 8, 9 the third column. Transpose matrices is nothing but interchanging the rows and column. This is an example. Next we see that upper triangular matrices. Here the square matrices is said to have an upper triangular matrix if all the entries above the principal diagonals are 0, hence Aij equal to 0. Whenever the condition is I less than j is an upper triangular matrices. Similarly, Lower triangular matrices. A square matrices Aij is called an lower triangular matrices if all the entries below the principal diagonals are 0. Upper triangular means above the principal diagonals are 0. Lower triangle means below the diagonal entries are zeros. Here the matrices Aij equal to 0 whenever I greater than j in a lower triangular matrices, whenever I less than j in an upper triangular matrices. We see that example. Below the diagonal entry is get 0. This is also in upper triangular matrices. Next example is above the diagonal entries are 0. This is called lower triangular matrices, including the diagonal also. And the upper triangular matrices means the diagonal and the above values are below the diagonal entries are 0. Lower triangular means above the diagonal entries are 0. This is also called an upper triangular matrices and lower triangular matrices. Next we see that symmetric matrices. A square matrices Aij is called symmetric if the condition is Aij is equal to Aji for all elements of I comma j. Skew symmetric matrices. A matrices A equal to Aij is called skew symmetric matrices if A equal to Aij's value is equal to minus Aji for all I equal to j. Symmetric matrices is nothing but A equal to A transpose. A square matrices A equal to Aij is called as symmetric matrices. If A equal to A transpose, the given matrices is symmetric matrices. Weak symmetric matrices is nothing but A equal to minus A transpose. We see that example. The given matrices A equal to 0, 3, 4, minus 3, 0, 7, minus 4, minus 7, 0. We convert this A matrix, we find that A transpose. A transpose means interchanging rows and columns. Here the first row is 3, 0, 3, 4. A transpose means the first column is 0, 3, 4. The second row is minus 3, 0, 7. The second column is also in A transpose minus 3, 0, 7. Here the value is minus 4, minus 7 equal to 0. Here the A transpose value is minus 4, minus 7 equal to 0. Check that condition A equal to A transpose, the given matrices is said to have a symmetric matrices. A is not equal to A transpose means is not a symmetric matrices. The second one example for skew symmetric matrices. A equal to minus A transpose. So here the value is just multiply the value for minus in the matrices of A. We get that 0, minus 3, minus 4, 3, 0, minus 7, 4, 7, 0. You have to check it. A equal to A transpose, the symmetric matrices. A equal to minus A transpose is also weak symmetric matrices. Next we see that some of the properties of symmetric and skew symmetric matrices. First one we see the symmetric matrices. Take any two symmetric matrices of order n. Here the symmetric matrices A and B. Take A and B be as symmetric matrices of order n. These are the properties of this matrices. A is a square matrices, then A is symmetric if and only if A equal to A transpose. Is already seen that from the definition. Next properties, A plus A transpose is again symmetric matrices. A plus B is also a symmetric matrices, that is sum of the symmetric matrices is symmetric product. AB is symmetric, then AB or a value is equal to BA. The third one is AB plus BA is a symmetric matrices. The last one is if A is symmetric, then K. The K is any scalar. K into A is also a symmetric matrices. These are the properties of symmetric matrices. Next we see that skew symmetric matrices. A square matrices A is a weak symmetric matrices if and only if A equal to minus A transpose. First we see the symmetric matrices, weak symmetric matrices. Next one, properties of the symmetric matrices. Next one is weak symmetric matrices. Next is Hermitian matrices. A square matrices A equal to Aij is called a Hermitian matrices if Aij is equal to conjugate of Aj bar for all Ij, that is conjugate value. Skew symmetric matrices, skew Hermitian matrices means a square matrices A equal to Aij Aij equal to minus conjugate of Aj bar, skew symmetric matrices. Next we see that the properties of Hermitian and pseudo-Hermitian matrices. Take any two A and B be square matrices of same order n. If you take A and B are Hermitian, the sum of the matrices is also Hermitian, therefore A plus B is a Hermitian. If A and B are skew Hermitian matrices, here also the sum of the matrices A plus B is also skew Hermitian matrices. The third property is if A is Hermitian, then the conjugate I into A is also skew Hermitian. Fourth one is if A is a skew Hermitian matrices, then IA is a Hermitian. First A is Hermitian, then we have to IA is skew Hermitian. If A is Hermitian matrices, then IA is a skew Hermitian matrices. The fifth one is A is a Hermitian matrices, K is any real number, then K into A is also a Hermitian matrices. If A is skew Hermitian, the same property is used for skew Hermitian also. If A is a skew Hermitian, K is a real, then Ka is also a skew Hermitian matrices. Both A and B are Hermitian matrices. Already we know that A plus B is Hermitian matrices. And the products, that is AB plus BA is also a Hermitian. If A and B are Hermitian matrices, the difference of the value is AB minus BA is also a Hermitian matrices. These are the properties of Hermitian and skew Hermitian matrices. Next we see that application of matrices. Application of matrices in various fields in real life, like that cryptography, wireless communication and computer graphics. I hope that you enjoyed this reading. Thank you for visiting this video. Thank you very much.